26 is highlighted?
I'm sorry?
Do you know if 26?
26? Let me see. Yes.
Okay.
Yeah, we'll get to that one. Okay, number 2. And go. Which of the following is true for a system whose equilibrium constant is relatively small? If we consider what the equilibrium constant is referencing with our model equation, then the equilibrium constant is going to be C and D over A and B. So reactants and products, if this is very small, if it's much, much less than 1, then we say that the product, the numerator is very small, the denominator is very large relatively. So that means the reaction favors reactants. The reaction doesn't proceed very well. It doesn't say anything about time to reach equilibrium. That's kinetics. We're not talking about kinetics here. If you look at equilibrium, actually, I'm introducing a topic here that we haven't got to yet, I don't think. But if you consider diamond, we think of diamond as very stable. Kinetically, it is. But thermodynamically, the equilibrium is way to the right. In other words, diamond should decompose over time, equilibrium speaking. But kinetically, it's going to take thousands and thousands and thousands and thousands of years to do it. Right? So there's a difference between kinetic explanation and equilibrium explanation. So A and B can't be it. So the equilibrium lies to the left, as written. Right? If we wrote it the other way around, it would lie to the right, because this would have to be flipped. If this is much, much less than 1, and we flip the equation, then the inverse of this would be much, much greater than 1. Depends on your perspective. How the equation is written makes all the difference in the world. Okay, let's see, number 3. For this equilibrium system, carbon dioxide plus hydrogen yields carbon monoxide plus water, and it has a enthalpy of plus 42 kilojoules per mole. K equals 1.6 at 1260 K, so it's pretty high temperature. If 0.15 mole each of CO2, H2CO, H2O were placed in a 1 liter thermally insulated vessel that was also at 1260 K, then as the system came to equilibrium, the temperature would increase or decrease. Okay. There's a lot of information there, and you don't need all of it. In order to answer this question, and we look at the answers, of course, the temperature would increase, decrease, remain constant, and then CO2 would either increase or decrease. So maybe I better write this one up here. Let's H2. These are all gases. They better be. Water's definitely going to be a gas at that temperature. And gases. And the delta H equals plus 42, was it? Kilojoules per mole. So what does that say about this equation? It's endothermic, because that's a positive. That means energy is going to be absorbed by the system to produce products. Okay. So K equals 1.6. 1.6, we're given that. We're given amounts of each one, 0.15 moles per liter. So each one is initially 0.15 molar all the way across. That's the initial. The question is, as the system comes to equilibrium, now, okay, maybe we do have to calculate Q. Let's do that. To see which way it's going to move, we need to know what Q is. All right, so we've got, these are all coefficients of 1. I think that's balanced. 2, yeah, it's balanced. So we would have 0.15 times 0.15 would be squared, and then 0.15 squared. So that's equal to 1. Okay. Q is less than K. If Q is less than K, that means we don't have enough product. It's too small. Okay. So the equilibrium is going to be established by moving that direction. That means that CO2 and hydrogen are going to be consumed. And part of the question, the answers are CO2 does something. So CO2 decreases. That means B or E. B or E is possible. B or E. Now let's look at the other conditions. Temperature would decrease. E, temperature would increase. All right. If, and we weren't told that we told the starting temperature, but we're not told that it's isothermal. Okay, so which side would the heat term go on? Well, this side. That. Okay, endothermic. So as these are being consumed, it's going to take heat from the system. So the temperature should decrease. And that would be B. Okay. Let's see, number 4. This side. Number 4. Addition of chemical B to an okay, 4 through 6 is referencing this equation. 2 A's, 2 B's, and a C. 2 A's, 2 B's, and a C. All gases, aren't they? Yeah. At the given temperature, the K is 1.6 times 10 to the minus 4. 10 to the plus 4, sorry. So we're favoring products at that temperature. So for number 4, addition of chemical B to an equilibrium mixture of the above would do what? If we had B, it'll shift this way. Right? It's going to consume some C and produce A. It would cause A to increase. Let's look at the others. Cannot be determined. None of the above doesn't work because we found one that works. Cause C to increase? No. C would decrease. A would increase. Now, what would happen to B? If we're going to add some B, right? Add some B, what would the actual value of B be at equilibrium? Well, some of it would be consumed, right? But not all of it. So in actuality, A concentration would increase, C would decrease, and B would slightly increase at equilibrium. Because we're not going to use all of it. Once we reach equilibrium, then the apparent changes stop, right? So in effect, we'll have a new equilibrium position. And the concentration here will be higher, lower, and a little bit higher. let's see. We're going to work on the same equation for the next one, I think. We're going to go down to 6. So 6 says raising the pressure by lowering the volume of the container will do what? For that situation, we need to know the number of moles. We have 2 moles in our stoichiometric relationship here, 2 moles here, and we have 3 moles here. So if we raise the pressure, if we decrease the volume, what's this system going to try to do? Make fewer moles of gas, right? Okay, we'll go back this direction. All right, so A will increase. That would be the best answer for that one is A. Let's see. Oh, 5. We didn't do 5. That's okay. Right. Let's look at number 8. A different equation here. Number 8 is working from, let's see, hexahydrocobalt CO and waters. This is a complex ion, 2 plus. Since water is neutral, then the cobalt, the charge had to come from cobalt. So this is cobalt 2. And then we have 4 chlorides. And the reaction gives us a different complex ion, 2 mites. Here we go, plus 6 waters. Now, did the oxidation state of cobalt change? This be 4 minuses and a 2. No, it didn't. It's the same on both sides. So all we did was exchange these chlorides for these waters. And when we did, we have, if this one predominates, it's pink. This one predominates, it's blue. And that's a question of perception. You know, when do you actually see the color difference? Physiologically speaking, you need roughly 10 times difference in concentration to see a change. But we don't need to know that to answer the question. Let's see. 8 says, which statement below describes the change that the system will undergo if hydrochloric acid is added? Okay. If we add that, then it's going to shift the equilibrium to the right toward the blue side. Right? It should become more blue. And, well, it can't become blue and pink at the same time. And the equilibrium will shift to the right. So A and C are good answers. And that's why we have E as the answer, 2 of the above. We're assuming that when we shift that equilibrium, that you can see the color change. All right. Number 9 is based upon 9, 2, what is it? H2 gas plus how many X's? Just 1. X sub 2 is in equilibrium with 2H2X gas plus energy. Plus energy. Okay, addition of X2 to a system described by the above equilibrium. If we add this one to it, excuse me, we're going to increase that one. Then what happens? Well, let's see. We'll cause this one to decrease. We'll cause this one to increase, and it'll get hotter. So what's a good example? A says H2 will decrease. Okay, that's right. B says X2 will decrease. No. X2 will after we add something, it'll decrease from that new position, but from the equilibrium position, X2 will be higher. So that's not it. H2X to decrease? No, it's increasing. Cannot possibly be carried out. I was searching for alternatives there. So A is the best answer for this one. Oh, while we're here, all these are gases, aren't they? Yeah, they're all gases. So what would happen for number 10 while we're here? What would happen if you added argon? We got 3 moles this side and 2 moles that side, but will argon have any effect on the equilibrium? No. Increasing the pressure with inert gases has no effect on the equilibrium because it does not alter the frequency of collisions of each of the reactants or the decomposition of the H2X, right? Argon's not present in that equation, so it has no impact on the reaction. Right. Get down, come on. Number 11. Which of the following statements is true? A, B, C, D, and E. Okay, when two opposing processes are proceeding at identical rates, the system is the equilibrium. Yeah, that's true. That's just a blanket statement for equilibrium. What about B? Catalysts are an effective means of changing the position of an equilibrium. What does a catalyst do? Speeds up a reaction. It just gets you to equilibrium quicker. It doesn't change the position of the equilibrium. So that's false. The concentration of the products equals that of the reactants and is constant at equilibrium. Not necessarily. The equilibrium position may give you lots of product and no reactant, or very little reactant. Just in a statement like that, all you have to do is find one exception and it's false. D, an endothermic reaction shifts toward reactants when heat is added. The heat term is on the left, right? So if you increase the temperature, it's going to shift toward products, not reactants. That's false. And the last one says none of the above. Okay, so that's false. So we found our answer. That one's 11. We're going to skip a few redundant ones. 14. All right, consider the reaction represented by the equation sulfur dioxide gas and oxygen gas is in equilibrium with sulfur trioxide, I'll bet you. Yes. Okay. For the system at equilibrium, okay, so we've established equilibrium. Which of the following explains what happens after the addition of oxygen gas? And assume the temperature is constant. So we're going to add this one. Add oxygen gas. The amount of SO2 increases. What happens to the value of K if we just add oxygen?
Would it say the same?
Constant temperature, nothing happens to it. K is constant for constant temperature, right? So that means A, B, C, throw them out. It's a contest between D and E, D or E. Test taking technique. No. Okay, so the last two said the amount of SO3 decreases. If we add that, SO3 is going to increase. So there's your answer. Take you all of 15 seconds. Okay, let's see. Speaking of 15, let's see, what do we got here? Consider the endothermic reaction. 2 bromine chloride yields 1 bromine and 1 chloride. And 1 chloride. And it's endothermic. So there you go. What's the effect? The first one is an effect, and the second one is another different effect. And then we got to find our answer that gives us the combination of the two. Changing the volume at constant temperature. If we change the volume at constant temperature, 2 moles and 2 moles, no effect. No effect for A. B, increasing the temperature at constant volume. If we increase the temperature, we're going to shift the equilibrium to the right and shift toward products. So B would be shift toward products. That would be the first, second, or third one. And no effect. So D or E, and shift toward products is D, right? That gets both of them. Let's see. We did one like that already. And we're going down, skipping a few, stopping at 20. Following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. So we have 2 mercury 2 oxide, and it decomposes, right? To mercury, elemental mercury is a liquid, and O2 is a gas. And that's balanced. And the delta H is a positive 43.4. Kilojoules, kilocalories. Kilocalories per mole. All right. We only care about the sign. The mass of HGO in the bulb could be increased by. All right. How can we increase this? Well, the equilibrium expression, right, KEQ, is simply O2. Because that's a solid and that's a liquid. So the only way we can impact the movement of this equilibrium situation is to affect the oxygen. That's the only way to move it. So removing some mercury, nope. Reducing the volume of the bulb. If we reduce the volume, we increase the pressure, and it wants to get rid of some of these to relieve that pressure. So B would be a good answer. B would be a good answer. Adding more mercury, nope. Increase the temperature. If you increase the temperature, so on this side, it goes that way. Okay, that won't work. Removing some O2, no, that would decrease the mass. Right, so that doesn't work either. B is the only good answer out of that whole bunch. All right, 21. At 500 K, 1 mole of gaseous ONCl is placed in 1 liter container. At equilibrium, it's 5.3% dissociated according to the equation shown here. Okay, so we're working from 2 ONCl. 2 ONCl is in equilibrium with 2NO, nitric oxide, and chlorine. And these are all gases. So at 500 degrees, so we're constant temperature. We don't have to worry about that one. What's the equilibrium constant? Okay, so we're going to need an ice table. We got to find out what the concentrations are down here in order to calculate the K. All right. We start off with 1 mole per liter. 1 molar, and nothing here and nothing here. Okay. We're told that at equilibrium, this has lost 5.3% of its value. Okay. So if that's 1, how would we lose 5.3%? Well, what's left over? 5.3, 100, 7, 4, 94.7% is left, right? So if it's 5.3%, then this lost 0.053. Right? So we had 0.053 molar there, and it lost 0.053 there. So does that add up if we use the decimal? Yeah, that adds up. Okay, how much did we gain on this side? Only half of that amount, right? Because the ratio is 1 to 2. So we're going to have, can I do this in my head? Half of that, 265 molar. Okay, so 0.0265 molar here, 0.053 molar here, and 0.947 molar there. So now we can do our calculation. All right, this is going to have 0.053 squared times 0.265, right? 265 to the first power. And then in the denominator, 0.947 squared. Okay. That calculator, unless you guys beat me to it. 0.053, and let's square it, and then 0.0265 times that. 0.947, square that one, and divide. Okay, if I did my math right, 8.30 times 10 to the minus 5. Yeah, A. Okay. All righty. Oops. Can I erase it? Ready? Okay. All right, let's see. Next highlighted one. We're almost to yours. 24. Nitrogen gas reacts with hydrogen gas to produce ammonia. Oh, where have I seen that one before? Fritz Haber. Hydrogen gas to produce ammonia. Okay, we have to balance the equation. And so I got 2 nitrogens here, the 2 there, that gives me 6 hydrogens. There we go. Now we're balanced. At 200 degrees in a closed vessel, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen. At equilibrium, the total pressure is 2.2 atmospheres. What's the partial pressure of hydrogen gas at equilibrium? So let's put what we know up here. Initially, what do we have? Initially, we have 1 atmosphere of nitrogen. And hydrogen is 2 atmospheres. Okay, we have no ammonia. Okay, at equilibrium, the total pressure is 2.2 atmospheres. So total pressure at equilibrium is 2.2 atmospheres, which is equal to what? It's equal to the partial pressure of nitrogen plus the partial pressure of hydrogen plus the partial pressure of ammonia. That's the law of partial pressures. Okay, let's see. Calculate the partial pressure of hydrogen gas. All right, what kind of change are we going to experience here? Well, we'll move that way, right? And we're going to lose some of this and lose some of that to produce some of this. So if we want to know the partial pressure of hydrogen, why don't we make it X? Well, actually, it doesn't matter. And the reason I say that is the partial pressure is going to be 2 minus X. If we make this X, and then we'd have to use fractions everywhere else. So why don't we make this one X? That means we minus 3X on this side. And this would be 2 times that would be plus 2X over here. Okay? So that's this side is 1 minus X, this side is 2 minus 3X, and this side is 2X. Okay. These are the final partial pressures of each of those gases, right? So if we add them up, that should equal 2.2 atmospheres, right? There we have an equation with one unknown. So let's see, we got 2 and 2 is 3, right? And then x's. We have minus 4x and a plus 2x is a minus 2x, right? 2.2. So now we say minus 2x equals 2.2 from 3 is 0.8, right? Minus 0.8. Did I do that right? I think I did. These minuses are going to go away. If we say x equals 0.8 divided by 2, right? Divided by 2 equals 0.4. That's what x is equal to. But the hydrogen concentration is 0.4. 0.4 times 3 subtracted from 2 is 0.8. 0.8 atmospheres. Okay. So we didn't even have to rely on the K value. We used the ice table to our advantage, but we didn't have to calculate a K because the way the problem was set up, we got an equation we can solve right there. All right. Next, 25. You were wanting 26, weren't you? Yeah. Almost there. Let's see. Initially, 2 moles of nitrogen and 4 moles of hydrogen were added to a 1-liter container, and the following reaction then occurred. Okay, Haber again. Yeah, I'll write it their way. That's a gas. That's a gas. And that's a gas. Initially, we had 2 moles of nitrogen and 4 moles of hydrogen. So 2 moles. How many significant figures? Just 2. In 1-liter container. So it's 2 molar. And then hydrogen is 4 molar. 4 molar. And this is nothing. Okay, the equilibrium concentration of ammonia equals 0.55. So we have a change and we have an equilibrium. And it tells us the equilibrium of ammonia is 0.55 molar. Okay. The value of K at 700 degrees for the formation of ammonia is. All right. How did this one get here? Right? You got there by adding that much. Where did that come from? Came from over here. Right? So if we produced that one and this one, we only lost half as much here. So we had 0.275, is it? Is that right? Yep. And this one is 3 times that size. So that's 1 and 21, 22, 2 and 6 is 8. I did my math right. Okay. So that means at equilibrium, we've got 1.725 molar nitrogen. And we've got 3. That's 5, 7, and 1 molar. So we should be able to calculate the equilibrium constant then. All right, so it's 0.55 squared over hydrogen's 3.175 cubed, and then nitrogen to the first power. That should give us our K value. 0.55 and square it, right? 3.175 and cube it. That would divide, and then 1.725 divide. So I get, let's see, we really only have 2 significant figures. So 5.5 times 10 to the minus 3. Yep. I didn't make any errors this time. Is this making sense? It's a procedure. It's a skill set. All right, now to 26. 26. Here we go. 26. Given the equilibrium constants for the following reactions, we have 2 of them, right? First one, second one. What is K for this system? All right. We're going to have to combine those equations and use Hess's law. Right? We can combine them, and then what do we do to the K's? Well, we've got to find out what the K's are for these 2 equations. Our target equation, which is the one I usually write first, is 2 copper solids and, oops, let down oxygen. Oxygen, like that. And 2 CuO solid. Okay, the first equation gives us copper. Yep, first one gives us copper and oxygen. But that first one, let me go ahead and write it up here. So number 1 is 4 coppers and then 1 oxygen yields 2 Cu2O solid, and it has a K1. All right. We don't need that many coppers. We only need half of those, right? So we're going to multiply this whole equation by 1/2. What does that do to the K? is the 1/2 power, right? 1/2 power. And that will give us 2 here, 1/2 there, and 1 there. Okay, that takes care of the copper, and half of the oxygens. The next one has Cu2O on the right-hand side. It needs to be on the left-hand side so we can cancel that term because this term is not anywhere in our target. Okay, so we're going to take I'm going to go ahead and flip the second equation. So it's Cu2O solid, Cu2O solid, plus what? Half oxygen is in equilibrium with 2CuO. Okay? And now the K2, because we flipped the equation, and we don't have to do anything else to it. Because there's only one of these and one of these, so they cancel. But we flipped the equation, so now this one is inverted. Okay. So we got this one covered. That one's canceled. These two together cover that one. And this one's covered. Okay. So we can put these together. So how do we put those together? Multiply. We multiply these values. So we have K to the 1/2 times 1 over K sub 2. That is 1. Now, which one even comes close? E, right? This is in the denominator. This would be equal to K1 to the 1/2 over K2, right? Does that answer your question? A little bit. Okay. Yeah, you have to scratch your head and go back to Hess's law. But then once you get them combined, you gotta say, all right, then what do I do with the results? You multiply them. Let's see. 28. What are we doing on time? 10 o'clock. What do we go to? 11:15. Okay, we're good. Number 28. Exactly 1 mole of N2O4 is placed in an empty 1 liter container, allowed to reach equilibrium based upon this equation. N2O4 gas yields 2 NO2s, right? Yep, 2 NO2. Okay, so the initial concentration of this is 1 mole per liter, right? Yep, 1 mole per liter. 1 molar. And nothing here. So we know it's going that direction to reach equilibrium. Okay, if at equilibrium, N2O4 is 37% dissociated, what's the equilibrium constant? Oops. Backwards. Change equilibrium. There we go. All right. So if we're going to dissociate this one to the extent of 37%, then it's lost that much molarity, 0.37, right? That means you get double that over here, plus 0.74 molar. So 0.74 on this side, and then 0.63 on this side, right? Okay, so we can calculate the K for this one. 0.74 is going to be squared, and N2O4 is to the first power. 0.74 and square it, and then 0.63 divided into that. and I get 0.87. Two significant figures. That's E. Okay. That's 28. Right, 29. Consider the reaction. Hydrogen and iodine makes 2HI. Yeah. All right, for which the K is 44.8. So K equals 44.8 at high temperature. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the equilibrium concentration of hydrogen. Okay. Let's see. This expression would be HI squared over H2 and I2. There we go. All right, so equimolar mixture of reactants gives the concentration of products to be 0.5, of the product to be 0.5. So if we set it up like this, then we know that this value is going to be 0.5 molar. But it starts off at 0. That means we had to acquire that much in the change, right? Okay. It came from this side, didn't it? So we lost half as much of this, minus 0.25, and we lost half as much of this, 0.25. So what we don't know is that, right? If these are equimolar amounts, then this would be X minus 0.25, and this would be X minus 0.25. Equilibrium concentration of hydrogen. So we've got to find out X and then subtract 0.25 from it, right? So 44.8 equals HI right? And then in the numerator, we have to the first power, X minus 0.25 and X minus 0.25. There we go. Okay, don't panic. It's not going to be a quadratic, right? Because what is this? This is squared, right? These two terms times each other squared. That means this whole thing, we can write it as 0.50 over X minus 0.25. The whole thing is squared. Okay? So if we take the square root of both sides, then we can get rid of the quadratic problem. What's the square root of 44.8? 44.8 square root. 6.693. So this is 6.693 equals this one over this one. Okay? Now what we have to do is get X on one side and the numbers on the other side. So let's bring X minus 0.25 over on this side. And that's 6.693X minus a quarter of 6.693. 0.25 times 1.673 minus 1.673, right? That times X there. And that leaves 0.5, oops, 0.50 on that side. Now we want 6.693 x equals 0.5 plus 1.673. Right? 0.5 added to that. 6.673. 6.67. That's not right. I added the wrong thing. Do this 0.5, 1.673. That's better. 2.173. My math okay so far? Okay, so now x is going to be this number divided by that number. 6.693 is 0.325. 0.325. So we want to know the concentration of hydrogen is X is this number minus that number. So concentration of hydrogen is equal to 0.325 minus 0.25. Okay. And that's 0.75. 0.75. That's not right. 0.075. Right? Yeah. That's in scientific notation there, so I converted it in my head. So this is the concentration of hydrogen at equilibrium. Oh, it's in scientific notation. 7.5 times 10 to the minus 2 E. Okay. I think I need a new marker. Put this one back here and make one of these out and see if they're. Don't need that. Okay. Number 30. Okay. Consider the following reaction. 2HF yields hydrogen plus fluorine. K equals 1 times 10 to the minus 2. 1 moles, 3 moles, mixed in 5 liter fast. Determine the reaction proportion Q. Okay. The reaction Q, I'm not going to write the equation up here. I'm just going to work from that equation and say Q is going to be the non-equilibrium concentration of product H2 to the first power, right? And F2 to the first power divided by HF squared. Okay. So now all we have to do is say, all right, in a 5 liter flask. Okay. So H2 is 0.362 divided by 5. Right? By 5. And then F2 is 0.75. 0.75 divided by 5. Okay. And then HF is 1 divided by 5 squared. Okay. Let's see here. I might as well let the calculator do most of the work. 0.362 divided by 5 is 0.0724. And then 0.75 divided by 5 is 0.15. Multiply those together. That's in my numerator. So the numerator, in case I make a mistake, I've got this 1.086 times 10 to the minus 2. And then the denominator is 0.2 squared, right? Yeah, 0.2 squared. Which is 4 times 10 to the minus 2. Divide that into that number. And I get 2.72 times 10 to the minus 1. Or 0.272. 0.272. That's B. Okay. Now, we're not given the K, so we can't say anything about which way it's. Oh, yeah, we are given K. All right, so if that's 0.272, it's greater than K. That means that mixture is moving back toward reactive. Yeah. All right. 31. Consider the following equilibrium. Okay, if the Kp value is 0.64, what's the equilibrium pressure of O2 gas if NO2 gas pressure is 0.52 and PNO is at equilibrium? Oh, that's pretty simple, actually. Kp is 0.604, right? So we're using pressure values. So the product side is NO, partial pressure of NO, partial pressure of O2. This one is squared. Yep. And NO2. Pressure of NO2. That's also squared. Okay. Now, we're given values. Equilibrium pressure of O2 gas if NO2 is 0.50. NO2 0.50 atmospheres. No, 520. 0.520. That's squared. Right? And NO is 0.3. 0.3 squared. And there's our unknown. That's fairly simple. We got an equation and one unknown. So, square this one and multiply by that one. 0.604 and then 0.52 squared times that. And then divide by 0.3 squared. And I get 1.81 atmospheres equals partial pressure of O2. Okay. All right, so let's see, 32. 32. And that one's getting weak. Let's say carbon disulfide and chlorine react to form S2Cl2 and carbon tetrachloride. Okay. Disulfur dichloride. When 2.14 moles of CS2 and 5.85 moles of Cl2 are placed in a 2-liter container, allowed to come to equilibrium, the mixture is found to contain 0.620 moles of carbon tetrachloride. How many moles of Cl2 are present at equilibrium? Okay. CS2, carbon disulfide. And that's very stinky. And that is deadly. I don't know about this one. It's probably not very healthy. Carbon tetrachloride is a known carcinogen. That's why they don't use it in dry cleaners anymore. The ocean, the EPA got together and said, we're going to ban that one. Okay, got set up right? Yeah. Now, 2.14 moles of CS2. This is initial, right? 2.14 in a 2 liter. 2.14 per 2 liters. So that's our molarity for that one. And 5.85 in a 2 liter for this one. That's its molarity. Allowed to come to equilibrium. So we're starting off with 0 there and 0 there. And we get a change and we get an equilibrium. All right. The mixture is found to contain 0.620 moles of carbon tetrachloride. 0.620 moles per 2 liters. Okay, so that's its molarity. Let me go ahead and calculate this one. 1.07. Yeah, 1.07 molar. And this one is 2.925 molar. Okay. And this one, let me go ahead and do this one. 0.310 molar. Okay, at equilibrium. And we're supposed to do what? How many moles of Cl2 are present? Okay, we need the number of moles present. Okay. So this came from somewhere. Right? And these are 1 to 1. So this one is 0.310 molar. And we lost the same amount from this one, minus 0.310 molar. And we lost 3 times that much for this one. So it's 0.930 molar. Okay. Okay. We don't need to use equilibrium constant or anything like that. We just subtract this from that one. That gives us the molarity at the end. So 930 subtracted from 2.925. 25 and 0.930. So this is 1.995 molar in 2 liters. This is moles per liter. So times 2 liters, right, is 3.99 moles. Okay. Hmm. 33. Okay. Let's see, at minus 80 degrees Celsius, K for this reaction is 4.66 times 10 to the minus 8. We introduce 0.047 moles of N2O4 into a 1 liter vessel. Let it equilibrium. The total pressure in the system at equilibrium will be. Okay, so we've got N2O, oops, that right position. N2O4 gas yields 2NO2 gas, right? Okay, the K is 4.66 times 10 to the minus 8. Now, what units go with this? That has to be in molarity because we're given moles and moles and volume, right? So 4.66, we have to say KEQ equals 4.66 times 10 to the minus 8, was it? Yeah. Okay. Initially, we start off with what? 0.47 moles of N2O4 in 1 liter. So 0.047 molar. Yeah. And the temperature, let's just write that up here. Temperature equals minus 80 degrees C. Okay, total pressure. What we need to know is how many moles of gas are in that volume. Right, this is 1 liter. Right, volume equals 1 liter. This is 0. So the change is going to go, right, this is going to be, it doesn't matter. We're going to lose some of that, and it's going to end up over here. 2x and then 0.047 minus x. So this is going to be 4.66 times 10 to the minus 8 equals 2x squared over 0.047 minus x. Okay. We could do the quadratic, right? Because there's no way I'm going to cancel the squared in this case. Or we can estimate. See, this value, 10 to the minus 8, that means almost nothing is going to be produced on this side. Okay. And if I do that, x is going to be extremely small. I can save you some time. This value says that x is going to be vanishingly small, which means eventually you're going to have 0.047 molar. Or in 1 liter flask, we're going to have moles equals 0.047 moles of gas because this is so small. Okay? Now, how are we going to determine the final pressure? We've got moles, we've got volume, we've got temperature, we've got our gas constant. We want to solve for pressure, right? So pressure equals nRT over V. Moles, 0.047. R is the one with liter atmospheres in it, 0.08206. Temperature is plus 273. Right? What's that? It's the simplest way. 193. 193 K. And then volume is 1 liter. Okay. So pressure is going to be the solution to that ideal gas equation. Now, this may not be, but it'll solve the problem. But if you're working in a lab and you've got to find the exact value, this is very, very cold temperature, right? So you may have to introduce your Van Hoff corrections. But for our purposes, we're going to assume that this ideal equation works even at that temperature, 1047. And then 0.08206 times, and then 193 times. So this is 0.74 atmosphere. Okay. Now we could have gone to the trouble and find out what X is, but X is so small, right? To two significant figures, it's not going to have any impact on that value. And that can save you some time in a test. All right. 34. 34. A sample of solid Ammonium nitrate was placed in an evacuated container and then heated so it decomposed explosively according to the following equation. All right. Ammonium nitrate, right, solid, right, produces N2O, laughing gas, plus H2O gas. Okay. At equilibrium, the total pressure in the container is 2.63 at a temperature of 500 degrees. Calculate Kp. All right. At equilibrium, the total pressure in the container is found to be 2.63. Okay. So we don't know what the initial is. We know there's nothing here. And at equilibrium, we know that this pressure, N2O, plus this pressure, H2O, equals 2.63 atmospheres. All right, at 500 degrees. So temperature equals 500 degrees C. Calculate Kp. Well, we know that these two are the only factors that are going to be in the K. Right. It's going to be N2O and H2O squared. All right. Oh, the stoichiometric ratio is the same as the pressure ratio, right? So there's going to be twice as much water vapor as there is nitrogen. That is, if we let this one be X, this one is 2X. So 3X equals 2.63, and X equals 3 into that. 0.63. 3 divided is 0.88. 0.88. And then 2 times that. So this one goes here. And 2 times that is 175. Equals 1.75. Okay, so we have our values now. N2O is 0.88. And this one is 1.75 squared. So I'm going to square that one. And times 0.88. So I get 2.71, that neighborhood. Yeah, 2.70. Close enough. Okay. Now, while we were here, I wanted to calculate what's the KEQ for this one. Right. We got the KP, and we know the formula is in useful information. I can't remember it. There it is. RT delta M. BP equals KC RT to the delta N. Okay, we know what KP is, 2.7. Let's use that value. KC is our unknown. R is the one with liter atmospheres in it, 206, times this one plus 273, right? So it'd be 773 times 773. And then delta N. What's delta N? it's 3 minus 0, right? Because we only have gases on that side. So this is to the third power. All right. So we need to resolve this one and divide it into 2.70. Let's see, 0.08206 times 773 and cube it. I get 2.55 and then divide it into 2.7. So if I calculate it right, I should get, no, that wasn't right. Let me do it again. 0.08206, okay, 773 times, and cube that. Oh, 2.55 times 10 to the fifth. That's what this is. Okay, now divide it into 2.7. And I get 1.06 times 10 to the minus 5. You have to take my word for it. The answer's not up there. Yeah. All right, let's see, 36. Fresh marker. Well, not fresh, but it's been sitting upside down, so it should have some ink in it. At a certain temperature, K for the reaction 2NO2 yields N2O4 is 7.5 liters per mole. Okay, if 2 moles of NO2 are placed in a 2-liter container and permitted to react, the calculate concentration of N2O4. All right, so 36. And we're going backwards. Previously, we had N2O4 decomposing to NO2 and N2O4. They're both gases. The K is 7.5. K equals 7.5. And that's equal to N2O4 divided by NO2 squared. Okay, what else are we given? 2 moles of NO2 are placed in a 2-liter container. So that's 1 molar. Initial is 1 molar. Equilibrium. So what's the question? Calculate the concentration of N2O4 at equilibrium. So we want this value right here. All right, let's make this one X. So we had to add so much of that one. That means this side lost half of that, didn't it? Minus X over 2. I saddled myself with a fraction, which shouldn't be too bad. So this is 1 minus X over 2. Let's get rid of the fraction. Let's make this one X. That means this one's no. Let's make this one 2X. Then this one's X. I had that one backwards, didn't I? Yep. So let's see. We add X to this one, then we're going to lose twice as much on this side. Okay, that's good. 1 minus 2X, and this is X. So this is 7.5 equals, and let's see. Calculate the concentration of N2O4. Yeah, we want that value. Okay, good. N2O4 is X up here. Down here is 1 minus 2X squared. Okay. This number is too big to discount X. X is going to be a substantial number, right? We can't count it out in this thing right here. So we're going to have to go quadratic. All right. So we're going to end up with, let's expand this polynomial first. 7.5 equals x over, so 1 times 1 is 1. 2x times 2x is 4x squared, right? And minus 2x times 1 plus minus 2x times 1 is minus 4x. Okay. Then we can bring this to the other side, and that's 7.5, right? And then minus 4 times that one is minus 30x, right? 4 times 7. 7.5 times 2 would be 15, and then times 2 again would be 30. That's why I put 30 here. And the same thing here, 30x squared. This is a plus 30x squared. And that's equal to x. All right, we gotta get everything on the left-hand side. So if we bring that negative x over here, it's 7.5 minus 31x plus 30x squared equals 0. So for our quadratic equation, this is A, this is B, and this is C. Right? And then let me get my cheat sheet here. X is equal to minus B, so plus 31, plus or minus the square root of B squared, so minus 31 squared, right? Minus 4 times A times 30 times C, 7.5. There we go. All over 2A, 2 times 30. Okay? All right, since this one is plus and minus, I want to resolve this one first and put a number up there. So 31 squared, and then 4 times 30 times 7.5, and subtract that from this one squared. And I get 61. Let me do that again just to be sure. 31 squared, okay. And then 4, 30, 7.5, and subtract 61. Okay. This is going to be 60. All right, so we've got 31. 31 plus or minus 61 over 60. So x could either be, let's do the plus first. 31 plus 61. 31 plus and divide by 60. Could be 1.53, or now we'll say 31 minus 61 is a negative, isn't it? Right, so it's 1.53 is x. And that is the number, that is the concentration of N2O4, isn't it? 1.53. Wait a minute. It's asking us, you're permitted to calculate the concentration of N2O4. Should be 1.53. All right, what did I do wrong? Are you following along in the work problems?
Yeah.
36. Tell me what I did wrong. Must be a calculation error.
I think so, because here you got x equals 0.647 or 0.386, and then it said
Wait a minute. Leave me alone here. Is this set up right?
Yes.
Okay. Is this set up right? X here, 1 minus 2x here. Did I do it that way? Or did I use a fraction?
Right.
Okay. And then this one goes here. Right. First power, 1 minus 2x squared, right? How about this down here? X over 1 minus 4x plus 4x squared. Is that right? 36. It's 1 minus 2x, that's right. And then x over 1 minus 2x squared. Okay, that's good up to there. Then 4x squared, 4x plus 1 minus 4x. Yep. And then x equals 7.5. See, 30x squared minus 31x. Okay, we're good down to the quadratic equation. This right here, that's good. So I must have made a mistake up there. Okay. Minus b should be 31. Yep. Then 31 squared minus 4a. Okay, that's right. And 2 over 30, 60. That's right. Okay, so I resolved the equation incorrectly. It must be. Let's do that again then. Okay. So everything's good up to that point. That's right, 60 there. How about this one? 31 squared. That's 961. 961. This is 120 times 7.5 is 900 minus 900. So that should be 61, right? 61. Okay. So the first one would be 31 plus, oh, it just dawned on me. What did I not do? I didn't take the square root. Okay. Let's see, 61 square root. Now we're talking. So this is 31 plus or minus 7.81 over 60. All right, now we're cooking. 31, let's see, minus that divided by 60. So the first possibility is 0.386 or 31 minus 7.81 divided by 60. The other possibility, I already did that one. Must be plus 31 here. This one's 0.647. Okay, which one makes sense? Well, let's look at this one over here. If we multiply 2 times this one, is it less than 1? Yeah. If we multiply this one times 2, it's greater than 1. Okay. So that one can't be. Has to be 0.386. And rounded off 3.39. Okay. Math error. Forgot my square root.